This is a presentation of the work of Prof. J.M. Manale. We're going to take a closer look at the equation that Euler had brought to the world and called his inspired guess, and that is the expansion of e to the power ix, where I is the square root of -1, and in this case, x is a real number. By this expansion, we can actually extrapolate then that e to the power I omega x would be given as follows. And the reality is that Euler has taken some creative liberties in coming to this result. So we're going to start by looking at how did he arrive at this result. Well, we first are going to look at the expansion of cos of chi and sine of chi using the Taylor-Maclaurin theorem. So there's our expansion of cos of chi, there's our expansion of sine of chi, and by that same theorem, we can then expand e to the power chi. And it's important to note that by the theorem, chi has to be a real number. And so what Euler does is he will now let chi equal to I times x. The important caveat here then is that if chi is real, then x is not real. X has to be an imaginary number. So now if we are going to make that substitution for chi, and now we are going to look at e to the power ix, we expand using the same Taylor-Maclaurin theorem, and we will group and gather terms, those that include I and those that do not, which gives us the following. So our expansion, e to the ix, is cos of x plus I sine of x. This looks suspiciously like we just said Euler's equation was. But the important caveat here is that Euler has said x is real, but we have just shown that x cannot be real. X is imaginary. So to illustrate the contradiction, we're just now going to look at cos of eta. So if cos of eta is given as being equal to cos of I eta, and sine of eta is equal to sine of I eta, then we do some algebraic manipulation, and we arrive at the following contradiction. Now let's look at our solutions to second order ODEs. So the exponent e to the ix is given as a solution to these homogeneous second order ODEs. And when we have that solution of y equals e to the power ix, we can actually get the first derivative and then the second derivative. From those two, we are actually able to rewrite our ODE as follows. And in this case, lambda is equal to omega squared, and it's a real number. So what were Euler's solutions? Well, Euler said we'll let y equal e to the rx. When we make those substitutions, we get the following. So in the first case, so he has three cases. We're going to look at them quickly. So in the first case, lambda is equal to negative omega squared, which gives us y sub 1 and y sub 2. And then we can combine that to get our solution for y. So in this case, a and b are constants. In the second case, we're going to say lambda is equal to omega squared. We now have an imaginary component, so y is equal to cos omega x plus I sine omega x. So we get y sub 3 and y sub 4. So here we have c and d as our constants. And then the trivial case where omega is 0, we have y is equal to ex plus f, where e and f are our constants of integration. So the solutions that we arrive at, we start the same way we did with our second order ODE. We are going to rearrange that just to isolate the second derivative. We're going to multiply both sides by the first derivative, and this allows us to use the chain rule to rewrite both sides. And now we're going to integrate both sides and simplify to arrive here. And here E is a constant of integration. So on the top right, I've just kept where we left off. We are going to then isolate y prime. And we're going to rewrite it as dy over dx so that now we can separate and integrate. And notice how I have manipulated the denominator. And that's what we get. Now, before we continue, we are just going to look at an aside. So if sine of u is equal to v, then if I take the derivative with respect to v on both sides, I will arrive at the following. du over dv is equal to 1 over cos of u. Now remember, 1 over cos of u is equal to 1 over the square root of 1 minus sine squared. That's using our trig identities. And remember, we had said that sine of u is v, so this becomes 1 over the square root of 1 minus v squared. So on the top right, I've kept where we left off with our original integration. And I am now just going to focus on the expression in the denominator. So that's square root over 2e over lambda minus y squared. We are going to rearrange that so that it looks something like what we had when we had our expression with u's and v's. Now, when I have this expression here, I'm going to make a substitution. I'm going to say v is equal to my y over the square root of 2e over lambda. And remember, we're going to say sine of u is v. So on the top right, I'm just keeping what we were working on in the first place. And I'm written down my substitutions that I want to refer back to. And now we're again just going to be looking at rewriting that left-hand side. So rewrote the fraction, which we now use to rewrite the integration, which we simplify. And again, as we continue to simplify, we have to remember now that v was sine of u, so I can make that substitution. And d sine u is actually cos of u du, which means what I had has simplified to the integral of du. So on the top right, I'm just reminding myself of the substitutions of v and sine of u. So we now have our very complicated integration statement now just says the integral of du is equal to the square root of lambda times the integral of dx. We integrate, so we get u is equal to the square root of lambda times x plus f. So remember, f is our constant of integration as well. And now we are going to reintroduce v by taking sine of both sides, because this gives us sine of u, which we know is v, and we can now make another substitution which allows us to introduce y. So we substitute the value that v is equal to y over the square root of 2e over lambda, and we rearrange, and we get the following. I have just introduced another variable phi, where phi is f over lambda. And that is where we will leave it. Prof does go on where he will take this case or this solution and then use that to examine the special cases and compare them with the cases that Euler had. Thank you.